Okay, in this module, we're going to continue talking about simple lenses, but we're going to look at different arrangements of the object, lens, and image to see what effect that has on the resulting image. And so I've left the simple diagram up here of our lens so that we can look at different arrangements. So for the first one, I want to look at a scenario where we have an A value that's less than the focal length. So again, A here is less than this length. So not the way that we've drawn it, but this is different. So what happens in this scenario is we have no real image. So if we put the lens into this scenario, no real image is going to exist, but we do have a virtual. And it's going to be magnified. So in this case, our eye has to be on the opposite side of the image. So I would actually be over here. So that's one case where we have a virtual magnified image. Okay, in the next scenario, we want to look at A is equal to the focal length. So again, you can think of this distance here being equal to this distance. What that's going to do is it puts us in a scenario where the image distance, that term we called B, is infinite. So essentially, this length B is infinite. So basically, the thing never converges. So these lines end up being parallel on the rear side of the lens, and so they never converge, and so we never have a real image because that's what we have in convergence. So no real image exists. However, this arrangement, even though we have no real image, can be useful. And what it's useful for determining the focal length. So we can actually use it to determine F. So in this configuration, this is kind of something we can do for calibration, for example, so that we can determine what the focal length is. Also, not important for this class, but it's how image formation for telescopes works. So that's just kind of a side point there. Okay, so we've looked at where they're equal. Now we want to look, as you can kind of tell, where A is shorter, same length as the focal, and now we want to look at scenarios where it is greater than F, and that's what I've drawn up here for you. So the first condition, and there can be multiple here, is that the distance A is between 2F and F. So I'll move this up. But again, think about the image that I've drawn in the previous. All right, so in this case, we're now forming a real magnified image. So these are the conditions that are starting to become important for us because we form a real magnified images. So in this case, the other quantities that are important, B is greater than A, right? Because again, we have magnified, so B is equal to A. So if we want to determine the magnification, we can divide B by A. So this is going to be important for our light microscopes. So this is going to be a real important classification that we want to look at. All right, when A equals 2F, so you can kind of see that 2F is an important length for these cases. So in this case, when they're equal, there's a real image, but it's not magnified because M is equal to 1, right? So what that tells us is that, again, the magnification was B over A, so that tells us that the relationship there and says that B is equal to A. And so the last one you can kind of see we're going through is now where we have A is equal, or sorry, A is greater than 2F. And so so we got a magnified image here, we got no magnification here, so as you might be able to predict, this gives you D magnification. But it is still a real image, so it converges at the focal point. And so M is less than 1. So effectively, this is not going to be a useful arrangement as you might expect, because we want to magnify the image, not make it smaller. So essentially, what we want to do when we're actually operating the microscope is really what we're trying to do is get to a situation where we have where we're basically in this realm, right? Where we have some value between 2F and F, because this is what we want to get. So when we're operating a compound light microscope, we're adjusting it such that we have the right configuration where A is going to be between 2F and F. So you can think of that's what's happening when we're adjusting the image here. So also, I want you to kind of think of the last time you used a microscope. You might have noticed that the specimen ends up being very close to the objective lens. And so sometimes that distance is very short, on the order of a few millimeters, right? So that kind of gives you a frame of reference for what these values of A, B, and F have to be. And so to get really high magnifications then we're often looking at distances for B that are on the order of many centimeters, right? So really close to the specimen, but the image ends up being centimeters away based on that magnification. So you can just play around with these numbers and see that on a microscope you use that's 100x, what these distances might be based on how close they are to the microscope. So like I said, these are for simple lenses. Later, we are going to talk about what objective lenses are actually composed of, what the inside looks like, and we'll see that it isn't a simple lens, but this is a good starting point that we can use to discuss these equations and so forth. All right, one last thing before we sort of move on to the next module is the magnification equation, which I showed earlier. I got it back here. Right? From this, you might suspect that you can put in whatever numbers you want, right? We can adjust the distances A and B such that this magnification has no upper limit, right? But if you're familiar with light microscopes, there is an upper limit. And so that's what the next modules are going to talk about, is how do we get from a simple magnification equation derived from the lens equation, and how do we learn and how do we understand what causes the actual upper limit here. And so that's what we're going to talk about in the next modules.